Waveguides Impedance series on Microwave Engineering, lecture number 1.60. In waveguide theory, we come across two types of impedances. One is wave impedance or waveguide impedance. Another one is characteristic impedance. The first one is useful in computing power flowing down the waveguide, whereas second one is useful while providing load matching to the waveguide. In the present module, we focus on these two types of impedances, their expressions. Now, let us move further to explore these two impedances. In waveguide theory, as already mentioned, two types of impedances. One is wave impedance, another is characteristic impedance. Values of these two impedances, they are dependent upon mode of the wave. Wave impedance is handy in calculating power flow, conductor losses, etc. Whereas the second one is found useful for load matching purpose. The CI, characteristic impedance, is brought from transmission line theory and is useful in fixing the load impedance for reflectionless signal delivery, that is for load matching purpose. Now let us focus on wave impedance. Wave impedance is denoted by ZZ. Z stands for impedance, small z is the subscript wave impedance. For waveguides, it is defined as the ratio of transverse electric field strength to transverse magnetic field strength. Mathematically, ZZ is total transverse electric field by total transverse magnetic field, E trans by H trans. Trans means normal to direction of propagation. If the waveguide is lying along z direction, wave journey is along z direction and normal to z direction are X and Y. So total transverse electric field means resultant or effective electric field of the components Ex and Ey. Similarly, transverse magnetic field means effective magnetic field due to Hx and Hy. In case of rectangular waveguide, ZZ. This first Z is impedance. This second Z subscript indicates the direction of wave journey. Wave journey here is along Z direction. Ex, Ey are, they become transverse components. Hx, Hy to transverse components. In case of rectangular waveguides, ZZ is E trans by H trans. It is equal to square root of Ex square plus Ey square by square root of Hx square plus Hy square. In case of circular waveguides, here also it is impedance, wave is traveling along z direction. In case of circular waveguides, normally we deal the problem issue in cylindrical coordinate system. Normal to z direction coordinates, normal to z are rho and phi. So E trans is square root of E rho square plus E phi square. Similarly, magnetic field transverse components are effective. Magnetic field is square root of H rho square plus H phi square. Fields in PPGs, parallel plate guides and rectangular waveguides, they are being given here. Hx, Hy, Ex, Ey. These are derived from Maxwell's curl equations. By manipulating Maxwell's curl equations, which are valid for a wave traveling along Z direction. These are obtained. One can see, for example, here Hx is equal to minus gamma by H square dou Hz by dou x plus j omega epsilon by H square dou Ez by dou y. Similarly, Hy, Ex, Ey, these are transverse components. Ex, Hx, Hy, Ex, Ey, these are transverse components. These are being expressed in terms of Hz and Ez. These are longitudinal components. In case of parallel plate guides, these same expressions, they are able to give Ex, Ey, Hx, Hy transverse components if you replace dou by dou y with 0. So general expressions, these are valid for rectangular waveguides. Same expressions, they become valid for parallel plate guide system also. Of course, you have to replace dou by dou y with 0. Now, if I want ZZ, wave impedance for a rectangular waveguide, I can substitute Hx, Hy, Ex, Ey in the defining relations that are shown in the previous slide. For parallel plate guide, if I want waveguide impedance, replace Hx, Hy, Ex, Ey in the defining relation shown in the previous slide. along with replacing dou by with 0. That is the idea. In case of circular waveguides, the transverse components are H rho, H phi, E rho, E phi. These are transverse components. Here also, transverse components are being expressed in terms of Hz, Ez, longitudinal components. Hz, Ez, Hz, Ez. These are longitudinal components. The only difference between fields in rectangular waveguides and fields in circular waveguides is that there it is in terms of reference to Cartesian system, whereas here the expressions are in cylindrical system. One can notice lot of similarity between these two. So by substituting Ex, Ey, Hx, Hy, the expressions that are shown in the previous slides in the defining relation of ZZ, one can find that it is wave impedance is omega frequency, mu means permeability by beta bar, that is phase shift constant along the length of the guide, which is of course eta by, can be shown it is eta by f. Eta is intrinsic impedance. Similarly, this is for T. For Tm, one can find it is beta bar by omega epsilon. This can be shown as product of intrinsic impedance with factor F. This is for Tm. Here F is square root of 1 minus Fc by F whole square factor, and eta is intrinsic impedance. It is given here, eta is square root of mu by epsilon. Note, eta is square root of mu by epsilon, whereas velocity is 1 by root mu epsilon. So in all the important parameters of wave theory, these mu, epsilon, sigma, they appear. That's why they are called constitutive parameters. Here, a graphical representation of the relation impedance, wave impedance, it has with frequency or wavelength is shown. When wavelength is equal to cutoff value for Tm mode, this impedance, wave impedance assumes 0. For T, it is assuming infinity. As frequency is increased from cutoff value, or wavelength is decreased from its cutoff value, what is happening is wave impedance is increasing for Tm. For T, it is decreasing. As frequency is increased further, or wavelength is decreased lesser and lesser values, what is happening is T impedance is falling, Tm impedance is rising. Ultimately, they both meet at one point, which is equal to intrinsic impedance, that is root mu by epsilon. That is about wave impedance. Now we move to another impedance, that is characteristic impedance. As already mentioned, it is this parameter is imported from transmission line theory, and its main use is in calculating the impedance of the load that accepts the entire signal without giving any reflections. Some more points we will discuss here. In transmission line theory, it is defined in several equivalent ways in terms of line voltages, currents, and power through the line. How it is defined there? Voltage, current, power voltage, power voltage. So using voltage, current, it is defined. Using power current also it is defined. Using power voltage also it is defined in transmission line theory. The definition is given like this: V by I. Z0 is characteristic impedance is V by I, or 2P by II conjugate, or VB conjugate by 2P power, where V and I are voltage and current phasors actually. P is also phasor, power flowing over the line when extended to infinity, and all are complex peak phasors or amplitudes, we can say. The point here is, when we use these definitions, all the three definitions give same value for characteristic impedance. You can use this, you can use this. Suppose voltage and current expressions are available, you can use this equation to find out characteristic impedance. If power and current are available, then you can use this expression to find Z0. If power voltage is available, this expression can give you the characteristic impedance. But the point is, all the three give same value of characteristic impedance when you are in transmission line theory. But here, when waveguide theory, the problem is these three definitions give give different values when applied to find characteristic impedance. That is the problem issue which you have to notice. All the definitions give same value for CI when applied in transmission line theory, but not so in case of waveguides. Main reason for this is that definitions are given in terms of voltages and currents, but in waveguide theory, voltage and current, they are taboo. They are not used. Only fields, electric field, magnetic field, they are the things with which we try to analyze waveguides. Because of this problem, compatibility, lack of appropriate or proper compatibility between voltages and currents with fields, this issue has come. The definitions are in voltages and currents, but waveguide analysis is in terms of fields. Lack of unique correspondence or compatibility between voltages and currents with fields is found as the main reason for giving different values by different definitions. In case of rectangular waveguides, for dominant mode, somehow we can calculate. If we calculate, you can find the definition. Voltage current definition gives characteristic impedance as pi by 2 B by A. This is wave impedance for T mode. Of course, this can be put in this form also. 60 pi square B by A square root of V R by epsilon R F inverse. F inverse 1 by F. F already defined. Square root of 1 minus that factor. It is already defined. FC by F whole square. Or you can put it in another form also in this way. It is 60 pi square. Pi square can be 3.7 into 3.17. That way you can convert this thing into a number. It is 600 B by A. Similarly, if you use our current definition, then what you get is a value for characteristic impedance, which is pi by 4 times the characteristic impedance which you got when you used voltage current relation, pi by 4 times. So difference is there. Our current relation, this is the voltage current relation. Some factor, they differ by, they are related through a factor. Similarly, one can find characteristic impedance using power voltage relation also. That is going to be 4 by 5 times characteristic impedance that is arrived at using voltage current relation definition. In case of circular waveguides for dominant mode, voltage current formula, power current formula, and power voltage formula respectively gives this. This is voltage current formula, power current formula, power voltage formula. One is 520, another is 354, another is 765. Of course, this factor is there by F. So different values. So naturally, a doubt comes, a question arises: what should be used? See, if you want to provide load matching, what should be the impedance of the load so that it gives reflectionless absorption, signal absorption? Shall we go for the first one or second one or third one? In practice, what they do is they used all these formulas to find out an approximate value of the impedance, and then using experimental means they go for finding the value of the load. So they take it as a kind of a rough estimate. These values, they take it as an estimate, and somewhere in between maximum and minimum, they try to fix the impedance by experimental means. So this is as far as impedances we encounter in waveguide theory is concerned. Enough.